So my name's Yannic, and I work at tipi.build by Angelo, where we do all sorts of wonderful things with build systems and tooling to make your life better. And as you can probably guess, this talk is going to be about tools, and it's really a collection of three things that I want to talk about. The first one would be linkers and overweight debug symbols, because that's somewhat of a recurring theme for us. The second one's build caching, and finally, a few tools I think everyone should know about. I hope some of you will get some of the references. I did my best to make them super obvious. So let's get started with debug symbols and the debug symbols guide to the galaxy. So the guide to the galaxy defines debug symbols as those curious little creatures that live inside your binary, quietly keeping track of what instruction did, what, to whom, and perhaps sometimes also why they did it. And the guide defines them as mostly harmless until, of course, you try to link a binary the size of a small moon. Less jokingly, when your binary is already sizable, just because you're wrangling a multi-million line code of lines of code project, dropping an optimization level, or just adding debug symbols to your build might just nudge you over that magical limit of about 2 gigabytes that the linker is using by default. And so now you can go ahead and tweak that by using the MC model switch and just put it to medium or large, and add a couple of other options that will ease your life to getting debug symbols work well when they get really huge. But this is just really hiding away some problem, because basically the linker is already screaming at you saying that I didn't sign up for this. And because really address mapping within the binary shouldn't be the reason whether you're having some optimization switch on or off, or being in control of whether you're having actual debug symbols or not. There's something quite simple we can do. We can have debug fission. So it's really telling the compiler to spit out all the debug symbols in a completely separate file and just add references to that file into your actual binary. And it gives you basically one DWO file per object file that the compiler outputs. And the binary itself now will get within about 10 to 15% of what it would be without any debug symbol. So that gives you a lot of room to breathe for everything else that you actually want to have in your binary. And we have had this for a decade now. Basically, with GCC 4.8 and Clang 3.8, 3.9, it's a thing. And it doesn't require any post-processing steps. It doesn't require any sort of additional setup in UCI to get going. It's super useful for when you ship your software, because you basically can give your customer the exact binary that you will be able to use during debugging, because it contains the references to that debugging information, but doesn't require to ship the whole set of debug symbols. And basically, there's a couple of other tools, like you see on the corner, where you can pack all the DWO files into a single pack, and that makes it quite easy for archival for the future usage at some point in time. And the rest of it, the debugging experience, is pretty much pristine versus what you already know. You just have to point it at that debug information. And in the words of the guide to the galaxy, debug fission is your towel. The answer to why is my linker screaming is really rarely 42. And it's probably just too many symbols. Use debug fission and don't panic. Now we have the galaxy thing behind us. And I want to go back from adventures in faraway galaxies at the other side of the universe back to England for the Great British Bake Off, build-off, actually. And this week's technical challenge is getting your cache right. And let's face it, caching is quite tricky in a multitude of ways in general. And when we're talking about caching in the context of builds, It's not really making our task easier because there's many small details to consider to make the cache both reliable and effective. The basic problem is really figuring out when you can reuse one cached artifact, especially when you have more than a single setup involved. So your computer is slightly different than your coworkers. That makes it really hard to reuse cache artifacts between those. And you need to balance this with actually also getting still enough of cache hits, because otherwise you're having all the trouble without the reward. So instead of going into nitty-gritty theory, I just wanted to give you a brief overview in a kind of a speed run of what we did to solve those problems, so you get an idea of one way to do it. The first step we do is to cut out all sources of variance that we can in the build. And the first step of it is that we create a clean, reproducible starting point for your build by mirroring your sources into a deterministic invariant location. So this ensures that the sources basically are at the exact same location for the build on everyone's computer. And this gives us a couple of benefits. It eases restoring the cache because you don't need to rewrite symbols and paths and stuff. And it also keeps everything always in the right place so that the rest of the toolchain, like your debugger and source code analysis, works just as is, because the things do not move between computers. The mirroring process basically yields a key, which is based on the contents of the sources that have been mirrored, and that key is used later on to access the cache. We do a bit of symlink magic on top of the whole thing so that you actually don't see that whole orchestrated dance of copying files. So your experience as end user basically remains the same. You still reap the benefits. We do kind of the same process for what we call an environment description. So that's basically a combination of a CMake toolchain. So our tooling is based on CMake. And a description or a specification of the specific execution environments that you want to run your build in. And getting your environment under control is really, really key here, because in the simplest case, what I just named the execution environment specification is a Docker file, basically, that contains all the instructions to construct your computer for the build. And it should contain everything, like tools, compilers, and whatever else you need. And now, if we're looking at what I just described, we start to have all the pieces in a good spot for having a reproducible and invariant build. So we have our sources in a known location, which doesn't change between computers. We have our CMake Toolchain file, which also lives in a known location, in a controlled location. And we have a container with all the tools. With that groundwork set, we can start to talk about the actual caching. And in our products, we combine a couple of those caches with multiple caches that have slightly different goals and modes of operation. So on the one hand, we have something we call the L1 cache, and that one basically stores entire build trees and install trees of your projects and dependencies. And we make them accessible in a version tracked way. Basically, we map your version control history to states of the cache so that we can pick the right one for your next incremental build, or to make your life easier when you're switching branches a lot. So you basically get to build from the closest possible base to what you did previously or one of your coworkers. The L2 cache, on the other hand, is something that operates at a much finer level of granularity. It basically caches the outputs of the build process by looking at all the inputs that are given. So that's all your header files, other objects, everything that goes into creating that one output is used as a key to make the artifacts accessible. And the real magic happens because we can actually combine these two technologies. And because the system also gives very strong guarantees about where the single translation unit is actually executed, it becomes possible to share caches between multiple very different execution environments. So be it you running your build on your local computer in the Docker container, or running the same build in a cloud resource, which runs the same image, or 1,000 cloud computers with tens of thousands of cores, and you can share the cache contents between all these contexts very easily, and it's really transparent to you as a user. So to finish this up, I promised just a couple of tools that perhaps not everyone is using, and I want to to start the next slide with a question. Who here has profiled their build recently? Oh, that's about the number I expected. So congrats to those who did. I would highly recommend you try this. And really, that whole category of tools is there to help you pinpoint the part of your build that is unbelievably slow and you have no real idea what it is. And the great news here is for everyone using Clang, you have the best tooling in the world. You get timing information on a per function in a translation unit level, and it's really easy to like nail down that one template instantiation that gives you headaches. GCC support for the same switch, which is F-time trace, is less advanced. I'm very hopeful they'll iron out whatever is missing, and I think it will get much better over time. On a bit higher level of abstraction, you can get some of the same information out of Ninja build logs, and there's tools like Ninja tracing that can give you a lot of the information very easily. And even our dear MSVC users are not left out. Microsoft ships VC-perf, which, while being a bit cumbersome to use, is very, very good in terms of the results it yields. And my recommendation is just do it. It's incredibly easy to get that information, and it's incredibly useful. And you'll know much more about what the compiler is actually doing in your build. And it helps you figure out whether you're CPU or IO bound or whatever it is. It's a goldmine of information. And the other thing is it will soon be available on our Enchflow platform dashboard as well. So basically, if you do use remote execution or CMake array, it will be just a click away. The second one is, bloated. Google chose, or the guy at Google starting this chose a brilliant name. It's a size profiler for binary, so it really parses your elf, conf files and tells you which sections and which symbols consume how much space. And it has one really awesome feature, which is it does delta analysis. So you can basically throw two versions of the same binary at it, and it will tell you what sections changed. And I think everyone should just throw that at the tail of their CI pipeline and have it always compare to the latest release that you actually did. You may need to do this on a debug symbol, strict release version, whatever, but it's super useful to catch hash embeds gone wrong very early or things like. It's quite wonderful when you're really asking yourself where that biscuit has gone. So my call really to all of you is level up your tooling game. It's a great investment in your time, in your happiness at the end of the day as well. And if I got you interested in what we do, the build caching and build acceleration tech, please come over, talk to us. There's Antonio here, there's Damien here, Florent is sitting back there. We can certainly help you with some of the heavy lifting and perhaps set you up for a free trial. Thanks for listening, and I hope you enjoy the rest of the conference.